So we start chapter 9 with sequences. You can see what we're talking about today is defining a sequence, arithmetic and geometric sequences, and graphing a sequence. We'll bring in the limits of sequences next class. So today's work is all things that you have seen before. Okay? I included this overview just because I thought it was kind of interesting. It's kind of telling us about the hodgepodge that is chapter 9. And it points out that we will be looking at L'Hôpital's rule, which is named after, I'm not even going to try, Guillaume Francois, what's that? Antoine de L'Hôpital. And he was given credit for this rule, even though he was not the one who first discovered it. John Bernoulli discovered the rule. And L'Hôpital was given credit because he was the first to publish. It all comes down to publishing. All right, so we will look at L'Hôpital's rule. We'll look at sequences and improper integrals. And that's all we have in this chapter. So let's take a look at what I would like you to do is get your text out instead of me reading to you and telling you these things. I want you to define the following terms using your text. The terms are sequence, finite sequence, and infinite sequence. Give an example of each and identify the second term of the sequence. We're somewhere around page 440, I think. So take a minute and then we'll go over these together. A sequence defined is what? Sam, what do you have?
A list of numbers written in an explicit order.
Yeah, so a list of numbers. Generally, I think of a list of numbers as a sequence. Written in an explicit order. There's some rule to it. There's some rule that's generating them. An example of a sequence would be something like 1, 3, 5, 7, 9. All right, and we call, if this is sequence A, then this would be A sub 1, 3 would be A sub 2, 5 would be A sub 3, and so on, and we refer to them as A sub 1 is the first term, A sub 2 is the second term, A sub 3 is the third term. The sequence that I've given here is a finite sequence. And a finite sequence is a sequence whose domain is restricted. Well, we need to make clear we understand what we're talking about when we say domain. Domain deals with the ends, not the actual terms, but the 1, 2, and 3, the index values. So in this one, I have A sub 1 through A sub 5, and nowhere beyond A sub 5. So my domain is restricted to go up to 5. So that's why that is a finite sequence. I could easily change that to be an infinite sequence by putting a comma and a dot, 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 saying that that sequence goes on forever. So that is an infinite sequence. Most of the sequences we'll be dealing with are infinite sequences. Another way to give an example of an infinite sequence would be to define a sequence by some rule. Let's say it was 2n plus 3. Is there any restriction on my n besides the fact that it should be positive integers? We generally don't talk about the negative 12 terms for our purposes. Okay, so otherwise, I can put in any n I want, any positive integer that I want for n. So that would be an infinite sequence. Okay? Sequences are usually listed in brackets. If you're not given a rule, listed in brackets with commas in between. So let me just put, for our infinite sequence, we have an unrestricted domain in the positive integers. All right, so given that, let's look at example 1. So defining a sequence explicitly. Two very important terms we need to understand. An explicit definition and a recursive definition. An explicit definition of a sequence is all in terms of n. So the example that we have here, a sub n equals negative 1 to the n over n squared plus 1, that is an explicit definition of a sequence. All I need to do is plug in a value for n to find the nth term. Does anybody remember what a recursive definition is from previous years, Samantha?
Well, you have to find the number before it to get the next.
That is the key. A recursive definition always uses the previous term to find the next term. So a recursive definition must use the previous term. So it would be something like a sub n equals a sub n minus 1 plus 3. So whatever your previous term is, you add 3 to it to get your next term.
So it's in terms of A.
That's the name of my sequence. It could be U, it could be B, or whatever. But it is in terms of your existing term. Okay? All right, so this problem says, find the first 6 terms and the 100th term of the sequence a sub n, where a is defined as that. So how would I find a sub 1? Plug in 1. So let's do that. We get our negative 1 to the first over 1 squared plus 1. And we get what? Negative 1 half. All right, well, if I want 6 terms, I would plug in 2. I would plug in 3, 4, 5, and 6. And then if I want the 100th term, I would plug in 100. So this is a good spot for us to talk about our calculator in sequence mode, because sometimes it's easier to use that. So take out your calculators, please. If it is a calculator active problem, sequence mode could be helpful, especially when you have to get 6 different terms. All right? You want to change your mode, if I can get there, to where it says functional, polar, parametric. Change that over to SEQ. And you want to change from connected to dot. That's mode, not made. All right? Then if you look at your y equals, you no longer have y. You have n min. You have what? U sub n min? Or U sub n? U of n. And U of n min. Correct? Okay. So, your calculator, I think, has room for 3 different sequences, U, V, and W. Our n min, we should talk about that. With sequences, n min, which is our first index number, is generally 1, unless we are dealing with time or money. And that's a general rule. When we're dealing with time or money, we'll start with n equals 0, a 0 term. Because we have some, like if we think about investments, we have some initial investment, and it doesn't grow until the end of the first year. So we start with time 0, and then have it change. But generally speaking, n min will be 1, so make your n min 1. Your U sub n, that's your formula, that's our equation. So that for us would be negative 1 to the n divided by, in parentheses, n squared plus 1. Like that. Our U sub n min, well, that is our first term when we plug in our 1. and we got that to be negative 1/2, so negative 0.5. All right, and then finally, before I go look at my table of values, I want to look at my table settings. So do second window and go to table set, I think is what it says, right? And generally speaking, if you want to see your whole sequence, you set your table start to 1. And what's next? What's after table start? Table step. Step will be integers as well, so step will be 1. And I would say put your independent variable on auto. Okay, and then go look at your table, which is second graph. Okay, so while you're working on that, let me help. Our first 6 terms we can see in our table, yes? If we want to know the 100th term, we would just plug 100 into the equation, or you can change your table start to start at something like 99, and go look at your table again. It just takes a little time to think. Absolutely, yes. All right. Okay, so any questions on sequence mode? Just a little reminder. All right, let's continue. Example 2, defining a sequence recursively. So the first one we did was explicit. Notice in this one, our b sub n, they need to give us a starting value, and they need to give us a recursive definition. B sub n is b sub n minus 1 plus 2. So if I want b sub 2, I'll take my previous term, which is b sub 1, which is 4, plus 2 gives me 6. B sub 3, 6 plus 2 is 8. B sub 4, and so on, is 8 plus 2, which is 10. Why do I need that n has to be greater than or equal to 2? We have, it won't work. Was this what you
have the n 0.
Oh, Boston, go ahead.
You don't have the value below.
We don't have the values. We're looking for our first term, and b sub n minus 1 would be b sub 2 minus 1, which is b sub 1, our first term. So they've given us our first. Anything else we would not have the value to solve for.
B0.
Right, we would not have b sub 0. Okay, there is no b sub 0 for us. Can you please continue on and tell me what b sub 8 is? This problem on the first 4, and then the 8th term. About 8. Okay? So using a recursive definition is useful if we're staying in the early parts of our sequence. Not so helpful if we need the 1000th term or something like that. All right, so let's find different ways to get these later terms. We move on to arithmetic sequences. Somebody tell me what an arithmetic sequence is. You've done this before. Andrew? Yeah. Yeah. It increases at regular intervals. We say it has a common difference between terms. Okay? If you graph an arithmetic sequence, what do you have? It's a line. Okay? All right. So what they're showing you here is an actual arithmetic sequence where our first term is a, our second term is a plus b, third term is a plus 2d, and so on. The recursive definition for an arithmetic sequence will always be a sub n equals a sub n minus 1 plus b. Again, we have that n has to be greater than or equal to 2. So we start with our first term. All right, so let's do an example, and we'll just do sequence 1. We won't be doing both of these. For each of the following arithmetic sequences, find the common difference, the 9th term, the recursive rule, and the explicit rule. So, for sequence 1, if I want the common difference, then I want to look at the second minus the first, the third minus the second, the fourth minus the third, and each time I get 3. 3. My common difference, D, is 3. All right, now for the 9th term. I don't want to have to keep adding 3 each time, so I'm going to think in terms of finding a rule or an equation of a line, right? So if I want to find a sub n, I can start with my first term, a sub 1, and I can add to it. I'm going to add b a certain number of times. So if I'm looking for the 3rd term, and I have the 1st term, how many times do I have to add b? 2 times, right? To get to the 3rd term, I add b once, and then I add b twice. So, if I am looking for the nth term, and I start at a sub 1, I add b times how many times? N minus 1. All right, so in our problem, we are looking for the 9th term. A sub 9 equals a sub 1, which is negative 5, plus our d is 3, and my n is 9, so here I will have 9 minus 1. And I get a sub 9 equals what? 19. All right, part C, the recursive rule for this, well, that means a sub n equals a sub n minus 1, then what? Plus 3. We want to remember that n has to be greater than or equal to 2. And then finally, our explicit rule, well, we started doing that up here in B, so let's finish that. A sub n is equal to, our a sub 1 is negative 5, plus our d is 3, and then we'll multiply by n minus 1. We can simplify that a little bit, giving us 3n minus 8. Basically the equation of a line. All right? So that's how we would do that for an arithmetic sequence. Let's quickly look at geometric. If there are any questions? Any questions on any part of this one? Okay. All right, moving on, let's do this for a geometric. So geometric sequence, they give an example here. The first term is a, the second is a times r, third is a times r squared. Instead of a common difference, geometric has a common ratio. The general recursive rule for a geometric is a sub n minus 1 times r. So let's look at our example sequence down here. We are going to find the common ratio, the 10th term, the recursive rule, and the explicit rule. So common ratio, please remember you're putting the later term over the earlier term. So negative 2 over 1, 4 over negative 2. Our common ratio is negative 2. 10th term, let's take a second and come up with our rule. A sub n is going to be the first term, a sub 1, times r to what power? N minus 1 again. So if we're looking for a sub 10, we've got a sub 1, which is 1, times negative 2 to the 9th, giving us negative 512. Someone tell me our recursive rule. A sub n equals a sub n minus 1 times negative 2. Good. And then finally, let's generalize our rule from B. For our explicit rule, a sub n equals a sub 1, which is 1, times negative 2 to the n minus 1. Are we all okay with the difference between recursive and explicit? Yeah. Okay. Questions on this one? All right, not much more today. Let's look at an interesting example where they give us parts of a sequence and we need to find the common ratio, the first term, and the explicit rule. So, we know that it is a geometric sequence and the second term is 6, and the fifth term is negative 48. Find the first term, the common ratio, and the explicit rule. Tell me what you did to solve.
I figured that in order to get to like negative 48 in the sequence, you have to multiply by the common ratio 3 times. So I solved 6 times e to the power of 3 equals negative 48.
6 times r to the power of 3?
Yeah, r to the power of
6
3.
times r cubed would have to equal negative 48.
Yeah.
Okay? And we get r cubed equals negative 8. So r equals negative 2. Very nice. And then?
And then I divided 6 by the common ratio to get first.
So a sub 1 is going to equal 6 divided by negative 2 to get negative 3.
And then I just plugged it in the equation.
A sub n equals negative 3 times negative 2 to the n minus 1. Perfect. I did it slightly differently when I did it. I thought a sub 2 is equal to a sub 1 times r, and a sub 5 is equal to a sub 1 times r to the 4th, plugged in values. And I solved the system to solve for r. Okay, just a slightly different route to get to the same solution. Any questions on that one? Okay. All right, all we have left then is just I wanted to point out that we talked about entering a sequence in sequence mode, and let's go ahead and practice graphing that. So I want to use the equation that we already have in our calculator. Go to your window and read off to me what's our first one, n min? All right, that is saying what term do you want to start with? And generally speaking, we start with our first term, so n min will be 1. And how many terms do we want? And max, let's say we want 10 of them, 1 through 10. Then you have plot start and plot step, is that what it is? Both of those can stay at 1. Xmin and Xmax, you want to make sure you have your window set so that we can see 1 through 10. So generally, you set it up almost identical to your Nmin and Nmax. So I'm going to go a little bigger just so I can have enough window to see the whole thing. Xmin of 1, Xmax of 15, Xscale of 1. The Ymin and the Ymax, we have to think about the values that will come out when we plug in our n's. And we already looked at our table, and we started with negative 0.5, correct? And the second one was 0.2, and then 0.0 something, negative 0.0 something. So let's look at a range for y to be negative 1, Ymax to 1, and let's look at y scale of 0.1. Go ahead and graph it. I think we end up with something kind of like this, and then again. I don't know if you can see any more of them, but this is what's happening. They're getting closer and closer to that x-axis. Okay, does everyone look like that? Okay, so that's how we can graph a sequence. In this example I included, they reference using parametric mode as well, which is another way to do it. I don't see why, I can't think of right now when parametric would be better than sequence mode, but if you're interested, you can go take a look at it. We will be graphing in parametric mode later on when we work with the calculus of parametrics, but just another interesting way to graph it. Okay? All right. Homework. Page 445, 1 through 23 odd. You can probably get most of it done. This is not a terribly long and involved homework. I will say, don't pay attention to any of the grayed out problems. Do them all with your calculator because you're finding 6 different terms, and I don't want you just sitting there plugging in by hand. So you can use your calculator on all of them. Okay?